Mike Bacidore, Editor-in-Chief of Control Design. And in this episode, I'm joined by Mark Arisman, Manager of Business Development for Control Products at Nord Drivesystems. And we're going to talk about drive technology and the digital twin. Welcome, Mark.
Thanks, Mike. Appreciate it. I'm happy to be here this morning. And I'm the Business Development Manager for Nord Drivesystems. I cover the United States, and I'm out there promoting our control products to the marketplace.
Being a drive expert then, let's start with centralized versus decentralized drive systems. Can you explain, well, what is a decentralized drive and how do decentralized drives differ from centralized drive systems in terms of installation, wiring complexity, and maintenance?
That's a great question to start off with, Mike. So just to explain decentralized drives a bit, so the classic drive in the control industry is in an electrical panel. It's considered an electrical device located in the electrical panel with all the other components, power supplies, PLCs, breakers, everything electrical that you would think of in that enclosure. So that's the centralized view. The decentralized drive is taking the VFD, the variable frequency drive, the motor drive, out of that electrical enclosure and moving it out onto the motor or near the motor where it's best to service that motor. So a lot of things change when you do that. And we're finding Nord has always specialized in that because we come at the control marketplace from the mechanical side of things. We're first a gearbox company, a motor manufacturer, but then also we come into the control world with the variable frequency drives that we produce. So when we move into decentralized, we're taking that VFD out of the electrical panel, putting it out on the machine or on the motor itself, mounted to the motor. And that brings some advantages, particularly in large footprint installations where you're covering a lot of geography in an install situation. It can lower your installation costs by minimizing the cabling and the wiring between components. So just as an example, when you move the drive out of the panel and you go to a decentralized solution, which is it's that same centralized cabinet mounted inverter that you're used to, but you're putting a more rugged case around it typically, getting some kind of IP rating or NEMA rating with that device. And then it's being designed to be located near the motor. The power connection can be picked up then local to the motor itself, rather than running the drive cables from the electrical cabinet that needs to be in a different location physically for all its reasons. And then we have problems where the cables can be too lengthy running from the VFD to the motor, right? That's a cable length situation that's covered by the National Electric Code. So you run into some complexity there. Moving it out near the motor gets rid of that problem, shortens that cable length. That's expensive cabling. You could save on the wiring related to that. Then when you do that, you can also use the VFD and its control element to pick up sensors or drive sensors or outputs local to where the drive system is. So lights and light curtains and pressure sensors and temperature sensors, all of those things that need to go into an installation. We have I/O points that are built into these decentralized VFDs to pick those up. That saves you cabling also for those and complexity, wiring that back to the electrical enclosure somewhere else.
Right. So the advantages, I mean, the cabling, obviously, big cost savings with that, but just the ability to have that smart device located closer to the motor, closer to the sensors, and being able to talk back and forth, another big advantage as well, right? So, and what kind of IP? I mean, what kind of ingress protection is typical for a drive that's mounted outside of the cabinet like that?
Yeah, typically with a decentralized drive, they're going to be IP55 kind of as a norm. So they are durable. You can get our drives come in IP66 flavors pretty much across our product range, but you can also go all the way up to IP69K for full wash down, chemical compatibility, say in a food and beverage situation.
Okay. Yep.
So you have lots of options related to that that can be quite durable. They could definitely be located outside if your drive unit is outside, say like in a construction materials environment that I was familiar with.
Sure.
They're quite rugged that way. You know, and
Right.
I do want to say the other thing, advantage-wise from a decentralized drive solution, is that when you move that unit all the way out of the electrical panel, it kind of changes the maintenance circumstance. Now you can't get, depending on the machinery you're talking about, yeah, it can be difficult to locate it near the drive system and have access maintenance wise, but in a lot of circumstances, it's easier because you're pulling it out of the electrical enclosure. You get away from arc flash concerns. You don't require a licensed electrician to service. Your maintenance person in the plant can look at that device and do some diagnosis right out on the machine level on the plant floor.
Right. No lockout, tag out. Yeah.
Yeah, not necessarily required. I mean, you could build
Right.
that, certainly build that into the system locally, but and then you can do local power down or zone power so that you can shut down just one drive or a series of drives and do maintenance on it while the rest of the system's up and running if you have that kind of
Right.
distributed installation.
Sure. Yeah. Big advantage for sure.
Yeah.
Well, given your background is as a machine builder back in the day, we won't
Mhm.
say how many days, but back in the day,
Too
uh,
many.
and when you were, what were some of the applications that you encountered where decentralized drives might have benefited the industrial system that you were designing and building at the time?
Sure. Okay. A great question. Yeah, moving the drives out of the panel, where I could have used that, I was in the construction materials business.
Right.
So we were manufacturing equipment that was installed in construction manufacturing facilities. And as such, every facility was different. So
Yeah.
if you think about what that means for trying to design a machine that maybe is modular, I need the electrical panel over here because that's where the service is, but I need the pumps located near the material I'm moving, which is way over here because I need to bulk refill the containers that feed that system, right? In that circumstance is what I had to do. So I
Sure.
really wanted in this case, it was pumps or other types of material conveyors related to this material. I wanted it over here on this side of the plant, electrical services over there, and then
Right.
dispensing point for that material might be in a third location that's removed. So how do you build a one type of machine that can be installed in a varying layout situation, and minimize that installation cost? So, if we save half a day of installation, that meant another system every week we could install in a facility. Our installation and service costs went way down if we could simplify, right? And I do think in those circumstances, I could think of a bunch of scenarios where if someone had been calling on me as a machine builder, selling decentralized drives to me actively and making me aware of the advantages, I certainly would have taken advantage of that. As it was, I put all my VFDs in an electrical enclosure, right? Like the norm, that was the norm.
Sure. Right.
I should have put them out on my pumps or conveyors out in the plant floor. I could have picked up electrical service out there, and that would have simplified my location for my equipment in those facilities. And in my case, this was 500 plus facilities across the country. So, like I said, installation service cost was a big deal for us.
Yeah, that's a big cost savings for sure. How long ago have decentralized drive systems become, I wouldn't say common. I mean, I think they're on the verge of being called commonplace at this point,
Yeah.
but how long has it been that this technology has really moved out of the cabinet and onto the machinery
Yeah.
where people are just totally comfortable with that?
Yeah. Nord Drivesystems has been manufacturing these for over 35 years.
Right?
So, they've been out in the marketplace for quite some time. I think that all of the material handling world has done a really good job of adopting this technology. And I
Sure.
think that's what's making it become more commonplace, to be honest, is the adoption from the material handling perspective, where, that's for Nord Drive Systems, that is definitely one big application area, intralogistics and material, tote handling, bag handling, package handling, that kind of thing, because those are those large footprint installations. That said, it doesn't mean it doesn't apply in a lot of other circumstances related to a pumping material, mechanical conveyance. In some cases, I was doing air conveyance, moving bulk material via air, right? Those circumstances where you're trying to move things from point A to point B, right? And it covers a good size of a facility. So I do think you're right. They've been around for some time. I think they're pretty commonplace. I don't think this is new technology necessarily to anyone, but I hope, through the conversation, we got some people out there that are listening and saying, hey, I didn't think about those things. I don't know why I do it the way I do. Maybe I should look at alternative scenarios.
Sure. Sure. Yeah, having anything in an electrical cabinet is just the way that those cabinets have been built for decades.
Yeah,
and
exactly.
It's only now that a lot of not just drives, but a lot of components are, seeing increased IP and putting them, where they need it, where it's needed, especially with a lot of edge computing taking place now. There's just a lot of things that don't need to go back to a centralized cabinet anymore, the way that they used to, at least.
For sure. Yeah, the communication advances. I think we're going to talk about that a little bit, but certainly the communication advances has enabled this technology maybe a little bit more than existed, say, 20 years ago.
Absolutely. You're right. Well, let's talk servo motors.
Okay. Sure.
Traditionally, they've been the preferred choice for high precision, high response applications. But how might an inverter affect someone's evaluation of switching out servos for induction motors?
Okay, that's a great question. Yeah, induction motor drive systems are cost effective related to servos. So that's the reason why we might even consider such a question.
Right. Yeah, absolutely.
Servos have are robust. They have their application for sure in high precision, high speed applications. So I think that in a bunch of different applications, we can consider when induction motors might push against that and become the more cost-effective solution. Sometimes I think servos are used because they've been used in the application that kind of move down the chain in terms of installation. So where you might move to an induction motor is when you can sacrifice maybe one or the other of speed or accuracy a bit, right? You can be quite accurate with an AC induction motor drive system. We put encoders routinely as part of our drive system package onto the motor, so we know positioning of shaft rotation down to a fraction of the arc minute. So the question really becomes then how does that translate to the gearbox ratio to the movement that's required for the application. You do have to take into account, maybe unlike servos, a little bit of backlash in that gear motor system. Nord has done some work to kind of quantify that as best we can for some applications, and we do have application specialists and engineers who can help with that determination, where how accurate is accurate enough for the application, given a total package solution of VFD motor and gearbox. How accurate can we be? How fast can we be? We can definitely be repeatable, for sure. So that's where the decision making for servo versus AC induction motor comes down to, how fast do I need to be, and how accurate do I need to be? If you can sacrifice speed a bit, we can get you very accurate because we know that positioning from our encoders that we read into our VFDs.
So the application dictates, what is possible, essentially.
For sure.
Right.
Yeah, maybe indexing applications, in food and bev or something like that. Maybe not, but certainly in the packaging part of that food and bev industry, for sure, it's something to consider.
Talking about inverters, how have frequency inverters evolved over the recent generations in terms of control features, communication protocols, and even energy efficiency?
Yeah, I think the first big advance was on the communication side. kind of what I was alluding to in terms of migration to field bus, where instead of hardware wired controls, you're moving to more advanced communications over some kind of Ethernet protocol, field bus protocol, Ethernet IP, Profinet, EtherCAT, something of that sort.
Right.
And what it does is it simplifies the ability to create high level communication. And then when we do that, we also raise the ability to gather data from what we're doing in the control system. So, all of our VFDs talk the common field bus languages. And as we move forward, I think the communication protocols are going to continue to migrate to higher and higher functions. We see a lot in terms of safety over Ethernet, functional safety over Ethernet right now, and what that can do in terms of simplifying the safety design of a control system. And then when we get to the data side of things, where the communication protocols are migrating to share more easily and readily data that's collected at a plant level, where you can do some analysis of that. That could be for efficiency of your plant. It can be for throughput analysis. It can be for predictive maintenance. So what's going on in my system? The data that I collect there can lead me to, where do I need to look from a maintenance standpoint? What do I need to schedule? What do I need to do in the next downtime that is scheduled? What needs to be looked at? So, we're moving towards higher and higher uptime expectations in some of these systems. And the only real way to do that effectively is to collect data so that you can predict when problems might happen and head them off before they do.
Yeah, the data has certainly changed. A lot of components, and just in terms of components being smart and the ability to share data. But then those network protocols certainly play a big part of that as well now, with the ability, whether they're natively able to communicate with one another or require some sort of middleware in order to translate protocols as well.
I think with frequency inverters and drive systems generally is moving efficiencies. Right. So, we're seeing migration right now from IE3 towards IE5 efficient motors. I think our European colleagues, and certainly we see that within Nord, are ahead of the curve there for obvious reasons related to power distribution and cost. But, nonetheless, when you move from IE3 to IE5 in those systems, and the VFD is a key component of that, right, in the control system, because at IE5, when you're talking about permanent magnet motors, you really need to you have to drive those with a frequency inverter to gain the efficiency that's needed. And then we're saving costs, we're running more efficiently. The total cost of ownership of those systems goes down. So I do think that's an advance in frequency inverters. That technology's been there, but I think it's being adopted right now. And we're just seeing that movement in the United States in particular, where more people are considering the higher efficiency standards.
Right. Okay. Well, speaking of advancements, what sorts of emerging technologies, maybe things like edge computing or AI-assisted diagnostics, or even advanced simulation, which technologies like that are being integrated into drives and inverters at this point?
Yeah, a lot of it's right now around that data collection capability we talked about a little bit, right? Where you're collecting condition data, right? So, for us, the control system, in the control system world, the VFD is a good data collector. All of the Nord VFDs have PLCs built into them, which have the ability to collect advanced data about what's going on with the drive system. So for those systems, control systems where, the mechanical driving is a key component, that's highly important. It can lead to analysis that allows you to be more efficient in your operation, increase the throughput, minimize the downtime. We're hearing more about companies that are our end users that are trying to go closer and closer to 100% uptime. They simply just do not want to afford downtime, even planned downtime in some cases, but certainly not unplanned downtime.
Right.
So again, the only way to do that is to gather the information from what's going on in the system. And then what you do, the emerging technologies really are feeding that information into the edge computing environment so that you have computing resources that are collecting the information, sorting through it, analyzing it, and feeding it to some decision-making process. Whether that's an operational engineer sitting there looking at the data, collect and deciding what to do, or using AI to do those diagnostics. I think all of that world is really coming together. It's a leading edge technology. I don't think we know yet all the advances we can make with it. I think people have good ideas. I think some standardization can help in that world. Because I see a lot of end users and integrators struggling with the costs that can be associated with such a thing, right? And the cost benefit analysis is sometimes difficult on emerging technologies. So I think as we get successes, you'll see a move more in that direction because it'll become more obvious what that return looks like. And I think in the process, some standardization will happen. So there's more interoperability between components. I don't have to work through that mess quite so much to get the return I'm looking for.
Sure. Do you think, I mean, given, I hate to call it a push, but given the trend toward more autonomous operations, and given that the ability to collect that data and have something like an artificial intelligence, expensive as that might be, to analyze that sort of data and reduce the amount of downtime in a plant, does that same sort of analysis enable more optimal manufacturing processes, or just to increase throughput or to optimize the operation that's already taking place, not just in terms of we want no downtime, but load sharing and just being able to optimize the assets that are being used in the manufacturing process as well?
Yeah, I think the more you can get your environment into that digital realm, the more you can do with it, right? And then before you make expensive changes in a facility, you can have a sense of what might be accomplished, right? So you can kind of, with existing infrastructure, you might be able to push the envelope a little bit, maybe delay some plant refinement. I'll take the opportunity to say something about maintenance again that we've talked.
Sure.
What's the point of the maintenance part of it? It's not just uptime. It's because in the industry, I think there's a challenge we have with qualified and experienced maintenance people.
Right.
And they're spread thin. So how do we make most effective use of the capability we do have in maintenance? Well, one way to do that is to feed the information, kind of collect it and feed the information to the people that can make the judgment about what needs to be done from a maintenance perspective, make them more effective. And I think that's the way to spread those resources a little bit thinner, simply out of need.
Right. Yeah, there's been a lot of talk about the retirement of the older maintenance techs and reliability engineers, and the story about the guy who can just walk into the plant and he can smell that bearing about to fail, right?
That's right.
Right. And that tribal knowledge is all going out the door into retirement, and how do you replace that without having people with 50 years of experience doing that.
Yeah.
But when you start looking at the ability of diagnostics assisted by whether it's artificial intelligence or whatever those algorithms might be, that takes a little of the burden off of those individuals, and that tribal knowledge just going right out the door. Let's talk about a little bit about advanced simulation then. Kind of
Okay.
shift gears, so to speak. See what I did there?
Yes.
So the definition of a digital twin, that's something, we could ask 10 people and we'd probably get 10 different definitions for that, right?
Yeah.
what would your definition be of a digital twin, and how are digital twins being utilized within the development and the commissioning processes? And what impact have digital twins had on reducing project lead times or improving reliability, like we've been talking about before?
Yeah. Yeah, I kind of simplify this one a little bit, digital twin myself, just because it's some kind of a squishy term.
Right.
It sounds
Yeah,
good,
absolutely.
but it's a little bit
Yeah,
of a
right.
squishy term, right? For
Yep.
me, what it means is simulation and modeling. How do we model our environment, our physical environment in a digital realm so that we can simulate it and understand it better without having to break things, right?
Right.
Without having to break things, because we're talking about expensive equipment, right? So we want to be as efficient as possible, but we also want to shorten development times and project life cycles and such. So, one way to do that, and I came from a heavy simulation environment early in my career in semiconductors, and, in that circumstance, you had no choice because you couldn't mess around with the physical realm. So it was a heavy simulation environment. I see that kind of scenario moving into the industrial world and the drive world, where we can model the function of, for example, our drive system, and provide that to a user. They can put that into their simulation environment, run the mechanical simulation that they have through a number of different software packages, and understand what kind of result they're going to get before it's even built. And that requires some assumptions, but you put that in place, and then as you install and commission, you have an expectation for what you're going to be able to achieve. And if you can model that side by side with the actual situation and see what's happening, and it can point you into problems or issues to resolve during the commissioning process to get you up to the right performance level in your system quicker. But really what it comes down to is the basics or the fundamentals of modeling electromechanical components and then putting them into that digital simulation environment.
Right. And then in terms of the reliability side, we're back to, again, the diagnostics and the maintenance practices that you're able to do just as a result of operating those digital twins. And
that's right. Yeah. When you have the ability to run it side by side, you can see what ideally should be happening. Compare that to what's happening in real life and say, hey, something's going wrong here. What is going wrong? Well, okay, now I got a modeling environment where I can point to something. And now we have an actionable thing to do from a maintenance standpoint. Go look at this thing. It's not behaving like the modeling environment tells me it should. Exactly. What's going on? As an engineer, did I make some poor assumptions? Or is a component not performing to expectations?
Right.
So it gives you a lot of avenues to resolve situations to get back to a reliable system quicker.
Right. Yeah, absolutely. And that, I mean, being able to make those diagnostics it's all based on the data, right? So
yeah,
what kinds of data or sensor inputs do you think are most valuable for building those accurate digital twins of, say, drive systems? And how important is that to ensure real-time synchronization between the physical and the virtual models?
Yeah, and we're trying to make our models as accurate as we can. It takes quite a bit of effort to do that. But our VFDs collect a lot of data. I would say even without external sensors to begin with, right? We're asked about that. So how do I know when my drive system's going to fail? How do I know when a bearing's going to go out or I got a lubrication problem, right? Things of that sort. And we're asked as experts in our drive systems, what do I need to be looking at? So, if you include our VFDs on there, you immediately pick up a ton of data.
Right.
Power usage, output current, field current, your torque current, temperature data from the motor, temperature data that's ambient, particularly if you have a temperature sensor that's wired in externally, temperature of the VFD, right? Is it overheating? You get error codes back from the VFD for its operation, the operation of the drive system. You could track runtime, real runtime data, actual usage time, days. See what's happening with your input voltage of the VFD, your average voltage coming in. Is that a problem? And, we have built up some information about our drive systems where, based on this information, a lot of it is runtime. We can recommend your lubrication change out or, lifetime on the lubrication that you're using. So that feeds into a good maintenance environment where I know what's going on here. And hopefully, the idea is if the model is accurate, then we're giving you a picture of ideally what should be happening. And then you're collecting the data through our VFD and feeding that into your data collection system on what is actually happening. And that gives you a good comparison point.
That trend has only happened, and correct me if I'm wrong, but because you're probably going to say, no, this has been happening for 35 years, Mike. But I believe that trend in collecting that data, from things like drives and being able to make inferences based on the performance of the drive, just information data that came from that drive that it was drive maintenance data before, but now we know it's indicative of other things like an imminent bearing failure or power consumption or whatever the case might be, inefficient, some other inefficient components that we might be able to see based on the way it's impacting the drive's performance.
Yeah.
It's only recent, right?
Yeah, no, we've been doing it in some regards for a long time, like you said. We've just gotten better at it over time.
Right. Yeah.
And we'll continue to push it. We know it's the right way to go. I would say this too. What I see is for users out there that are like, well, that seems like a bridge too far in my system. My hardware's antiquated and blah. I know, but start gathering data. The data that you can gather in the system you have. Take the upgrades you can make to gather more of it. It's not always obvious the advances that can be made because I think there's sometimes the wrong assumption that I need to make a huge investment, overhaul everything to move to the new environment where I'm collecting a ton of data. You can make advances in an existing system with small equipment upgrades, small technology improvements. Once you see the return, okay, now you can justify something, on your schedule, what you can do in your situation based on your return that you see. But collecting data, it will pay dividends.
Sure. I know traditionally switching to a VFD, like the main advantage was, the energy efficiency, of course, the savings is undeniable. But has that shifted, or is that kind of that entry point where, yep, we can show a win by increasing the energy efficiency, and now look at the data we have and look at the additional benefits that we can realize because of that?
Yeah, I think the world has they know that the world knows the advantages to having a VFD. And all just starting from protection of your investment in your drive system. Right. It provides all these protection capabilities in there, controlling ramp up, ramp down, just simple things like that to begin with. And what we've seen is the inverter prices condensed to where, going to a direct online kind of situation, the cost differential has become minimized. And then if you're selecting more advanced VFDs in the process, you're also picking up, like we've been talking about, all the extra data collection.
Yep.
So, the advances and the cost reduction has led to a situation where you should be using an inverter to protect your motors no matter what. When I was doing plant level stuff, I definitely did that. I assumed I was going to have a VFD in my system because as a control engineer, I needed to see what was going on. I wanted to protect that and the investment we had in that drive system. So I think that has done a lot to move the ball forward. So